we are set now. This is a work I've been done with the kernel guys to speed up getrandom with a cryptographic primitive on the kernel, so we can get it faster on the userland. And to understand why we did it and how we did it, I will provide some API history on how the Linux provide entropy, the ways that we did, and we experiment on glibc and the mistakes we did, and then the attempt to do this, and how we end up with a vDSO symbol, and then the vDSO symbol, how it's implemented both in the kernel and some performance numbers. So the Linux API has evolved during the years. So, and we need a good entropy because the kernel use this on itself, and the userland uses on a lot of places. And people do tend to re-implement this using either good libraries or rely on the kernel. And to provide a good entropy source, it's not an easy task. The kernel itself evolved during the years, and it did some mistakes. It was fixed, and to provide a not only easy and not only good source of entropy, it needs to be fast as well, because people will end up relying on this. So that we get the getrandom on Linux 3.17. It was added to overcome two essential issues with the dev urandom, which is if you do not have more file descriptors available, and how you access this without procps or the devs device file system replicated on either on C-root or your container. And then the Linux also changed the dev urandom to not block, because they found out on some system when you boot on the specific scenarios, it can be a source of trouble. And Linux 5.5 changed the dev urandom to behave more like a getrandom, so you don't have different APIs providing different entropy manner. And this is more recent changes that Linux did. Linux 5.17 added a mechanism so VM forks could reseed its cryptographic secure random number generator. The idea is to avoid the VM snapshot when you duplicate or you stop and resume VMs to see the same entropy pool. So there, later, on the same release but on different commit, it also added a per CPU state with some extra cryptographic hardening. And the idea is to improve multi-core performance. So you have a per CPU buffer where if you have multiple process querying the getrandom or the urandom, you do not take a lock on most of cases. And finally, you have Linux 5.18 that improved the urandom initialization, where if your CPU provides, it will query some CPU cycles counter to initialize the entropy source or the entropy pool. And finally, which is really recently, Linux 6.11 added the vDSO getrandom implementation, which is it is tied to the kernel interface, but it provides a user-based solid implementation. So while the three first points, it's more a kernel change over the years, the last one, it's only userland change that aims to provide a better latency. And we have rely on userland. What I mean here is the libc used on most Linux systems. We've been relying on entropy and randomness. We have this atrandom, which is a very limited pool provided by process, and we use this on both stack guard and pointer mangling initialization. But it's very limited, and we need something else to add internal hardening or to provide a better way so userland can query entropy. So we added the getrandom syscall wrapper, and we also added the getEntropy, which is just a BSD or symbol, and it was based on getrandom. So it basically it's the getrandom that was the new thing here. And finally, on glibc-36, we provide arc for random. The arc for random was is a symbol from BSD. It's used in a lot of BSD projects, and the idea is different than getrandom. It should always provide entropy, and if it cannot provide entropy either from the system, from syscall, or for some other source, it should abort. And because the idea is this is used on some cryptographic primitives or cryptographic system, so if you require entropy, you need to get it. And then this is the initial point that starts all the discussion, and if you should provide a vDSO and all the problems with the approach that we did on glibc. So the first time we tried to provide something similar to getrandom on userland, it was on glibc-238. Florian Weimer from Red Hat added a very complex implementation based on AES. It was more oriented for x86, so it used the cryptographic instructions. It has a very complex fork detection where it creates a shared memory and using atomic operations. So it was very hard to reveal this. But at least it was lockless, meaning it had per thread buffers, so it should be fast. It was fast, and it's a signal safe. So the idea is you can call it on a signal handler. The problem is the patch stalled, and it was not applied in any implementation. Later, I took the job and proposed a similar implementation, but based on the OpenBSD one. It was much more simpler. The Cha-Cha implementation is a much more simple implementation than AES. It has limited fork detection, so it didn't have the complex shared memory way. Either we support med fork, wipe on fork, or with supported fork handler. And I also took the liberty to add some optimization for some architectures. And after some iteration, it was committed on 236. The problem is, just after we committed, Jason Dornfeld, the Linux handle maintainer, raised multiple concerns about this approach, which is, since it is a solid user-based implementation, it does not have enough information on how to receive the cryptographic security state. Meaning, if you rebinate, things will go wrong because you can leak information. The implementation also does not have too much care on how it plays with memory. So it was insecure by design, according to him. And then after some discussion and some back and forth, we decided to revert this implementation. And arc for random was implemented using just get for random. So it was a syscall in the end. And when we finished this and released glibc-236, users complained that it was too slow. It was too slow because other systems like BSD, OpenBSD, FreeBSD did not do this. It was userland solid implementation, and it was way faster, especially for small buffers. And this was from an NTP daemon that it was very simple, but it requires some randomness, and it uses arc for random when it's available. And when it started to deploy, it saw a very large increase of syscalls, and it was about 25% of performance decrease. So we have some results and some history from the experiment where users expect that the arg for random, get for random should be a cryptographic secure RNG. So they will use this for cryptographic primitives, key creation, and things like that. So the user space implementation should provide the same security guarantees as the kernel. If you do not do this, there is no good reason to do this in the userland. We just do this on the kernel. And another main point is we need good performance, which is low latency and a good throughput. So Jason and myself, we thought which is the better way to do this. And the whole idea is we need the main part of the algorithm to be in the userland. We need to avoid syscalls, but we need a way to communicate between the kernel and the userland when the cryptographic buffer needs to be received. And we need a way to the system to not swap this memory, to not swap the cryptographic state. And we need to handle memory pressure, where if the memory, this buffer needs to be dropped, it can be dropped safely. And it cannot be unlocked. So this turned out to be a new map flag, map droppable, which was implemented first. And then we also need to be similar to the kernel. It needs to be lockless, or at least a way to implement this through a lockless implementation. So we need also some userland work on the libc to accomplish this. So this is a general block organization, how the kernel does this. We have the vDSO, which is a vDSO with VVAR, which is mapped on each process, which contains the implementation, the kernel get random symbol, which has the cha-cha implementation. And we have a VVAR, which is a page that is mapped on each process but shared across the system. And the kernel device driver, it accesses the VVAR, and it advertises when the state needs to be received and when the crypto state is ready. And then the userland can access the symbol with some defined API to get the entropy from the kernel. So basically, the kernel is the one responsible to advertise when the crypto is ready and when need to receive it. This is the main point of doing this as a vDSO implementation, because otherwise we need to query the kernel when the things are ready. But the idea is to let the kernel know asynchronously, and this is done by the VVAR data page. We also have some considerations on how to implement the cha-cha 20. Jason said that it's debatable, but his idea is the implementation should not leak any information on the stack. So the implementation should not use the stack at all. And it requires a specific, art-specific implementation, so we cannot use the one from the kernel. So each architecture needs to implement its own. It's a very simple implementation, but either way, you need to take care of this extra constraint. And on the userland side, it's very, very simple. We keep this CSRNG state, which is allocated using this map droppable special flag. And we keep a per thread state that when user create new threads, it will just get one of them. And we have some extra metadata to keep track of this extra state. So nothing really fancy. I don't want to implement a new memory allocator. So the idea is how to keep track of all this stuff without adding additional burden. We need some extra care for some things for the API, but the idea is to keep it simple. So the kernel API provides a way to query the state that it requires, because the idea is to not tie to a specific algorithm. The userland has no idea that it's cha-cha-20. It can be anything. The kernel can change this in the future, can change the state size, can change the algorithm, can change even the mmap flags required. So the glibc or the userland do some initialization to query the parameters, and on the getrandom, we try to allocate a state, and we need some intrinsic handling. We call the vDSO and release the state. It's very simple. It's 100 lines or even so. And with this data structure, we can provide per thread list. We mean the fast path is lockless on most of cases. So on the first call, we need some lock because we need to allocate this metadata. But after the thread get the initial state, it can do this without locks. So it's fast on multi-thread environment. And we had to add some fork handling, which is one of the worst case scenarios. But either way, after fork, it should work, although it might leak some internal state. So let's go to the performance number, which is the main reason we did this. So this is a kernel benchmark that Jason has done to evaluate how it works. And it allocates small buffers, which is the idea of the most user case scenarios. And you can see it has a 10-fold performance improvement, both on single and multi-thread. And at the same time, I did some experiments to see how it plays on throughput, where you increase the buffer size and comparing to the syscall. So you can see that after some size, the kernel provides a better throughput because the syscall overhead becomes minimal, becomes amortized during time. And it's mainly because the kernel uses a more optimized cha-cha implementation that one we provide on the vDSO. But even though there is room for improvement, and you have good throughput even using the vDSO implementation. And how are we going to try this? You need a Linux 6.11 for x86 or 6.12 for ARM64 and other architectures, glibc 4.1, and hardware with Neon support. I think Ubuntu 25 and Fedora 42 should be the first distros that provide this support upstream. And that's all. Any questions? Okay, thank you.